No problem. Good morning to anybody else who's on the West Coast. Um, and thank you to Cilian and Matteo and Ennie for continuing to organize this course every year. I think the community really appreciates it. So I'm going to tell you in 15 minutes or so about Pinpoint and in general about trajectory planning. Um, I do want to mention right away that a lot of this talk is redundant because we do have a nice website with a whole bunch of tutorials that walk you through almost everything that I'm going to tell you this morning. So do watch those videos and look through those tutorials on your own time. I think you'll find repeats of everything that I say, and hopefully those resources are helpful. Okay, so just to start off, Pinpoint is a 3D space that helps you orient yourself relative to the mouse brain, the rat brain, and soon many other brains. Place probes in that space to understand their geometry and how they're going to fit into the brain and how they'll reach the targets that you're trying to get to. And it's a tool for seeing and learning a little more about the brain as you're staring at that. Sorry, let me move the thing around. Okay. So what you're seeing here is the view that you'll see inside of Pinpoint when you load it on the Pinpoint website. This is the mouse brain pointing anterior. So the olfactory bulb is here and the cerebellum is in the back. These probes here are the original 1.0 neuropixels. And in Pinpoint, you can see that there's sort of a white region on the end of each probe. This is the active sites that are currently set to record. And those are shown on the left here as well. So this sort of purplish probe is the one on the left. And you can see that it's running through a visual area, through the hippocampus, and into the thalamus. On the right side, there's sort of a in-plane slice view through the brain, in plane with the electrodes. And then there's some other tools which we'll talk about later. The most important of these is this set of coordinates here on the right side, which are the surgical coordinates shown by this little blue ball here that you'll need to actually perform your recording. And I'll go through this all a little more in the demo in a few minutes, but just wanted to give you a quick orientation to the view that you're going to be seeing in Pinpoint. And I think it's worth spending just a little bit of time thinking about like what are the actual, like why do we need this trajectory planner thing in the first place? The goal for Pinpoint and the point of using this tool is that it's going to give you coordinates for your insertions relative to some reference coordinate. So on the mouse, that's going to be bregma. You're going to move your probe to that reference coordinate, calibrate your manipulator or your stereotax, and then you're going to move relative to that to those insertion coordinates. And that's the reason to use Pinpoint. If you're just aiming for some random area in the brain, you don't need a trajectory planner, although it might be helpful for knowing where you are in the brain. The other reason to use a tool like this is that it really helps with brain anatomy. I came from humans when I first started doing systems neuroscience, and I tended to just drive straight down into the hippocampus because I didn't realize that cortex in a mouse is quite thin. But with a tool like this, you know where you are live while you're doing your recordings, which is really helpful. Another goal for a trajectory planner is that with Pinpoint, you can save information about where you are, and we can put safeguards into Pinpoint that potentially prevent mistakes like driving straight into the hippocampus instead of in visual cortex. And the last one I'm going to spend a little bit of time today talking about is that we've started really building a lot of automation tools into Pinpoint. And the point of doing that is that it frees your time to think about data quality and analysis, and sort of takes you out of the rig, which I think is really helpful for people to have sort of more perspective on, like, is the data I'm getting good, instead of just, am I getting to the region that I'm getting to? We can handle that for you and let you think more about those sort of meta experiment questions. Okay, so I'm going to do a quick demo of Pinpoint itself. And the point of this, of course, is that one of the homework assignments is for you to plan a trajectory. I have a suggested trajectory that I'm going to plan live now in the demo and that you can do again. But actually, I think you should plan a trajectory that is actually meaningful for you. But do this one first so you kind of know where you are. This trajectory is the repeated site from one of the International Brain Laboratory papers. And I'll have a slide at the end and I'll post it on Slack so that you have a copy of this as well. All right, so to get to Pinpoint, you would navigate to our website, data.virtualbrainlab.org/pinpoint. And when the page loads, you'll see something like this. So right now I'm left clicking with my mouse in the scene here. And if I move the mouse to the right or to the left, forward or up or down, you can see that what am I doing? I'm rolling the brain or pitching the brain. There's a bunch of orientation axes shown here in red, blue, and yellow, and also copied up here, yellow, red, and blue, to help you orient to the orientation of the brain as you move it around. You can also scroll with your mouse wheel in and out to zoom on the brain. This little ball is also right now placed at bregma by default. And again, this is the mouse brain. Okay, so to plan a insertion, what we're going to do is add a new probe into the scene. I'm going to drop the 1.0 probe that I showed you before. And if we zoom out a bunch, we can see sort of the scale of the probe relative to the brain itself. Right now, the probe is at 0, 0, 0 in AP-MLDV space, and it's placed right at bregma. The recommended way to plan an insertion, and I think, is to look for a region that you want to target. So for example, in this, sorry, if I go back here, one of our targets here is PO, and I'm just going to switch a setting on here. Whoops. Okay, we're going to search for an area. Oh, I guess I can't pull up PO. That's okay. We'll go through one of the Viz-A regions in the front. So you can search for regions on this side area. You can snap the probe to them. And that's what I really wanted to show you, is that you can pull up different regions, Viz-A maybe, or Viz-P, and snap the probe to the center of that region. And that's going to allow you to drive the probe down to a target region without having to necessarily know exactly where it is ahead of time relative to that reference coordinate. So once you've done that, you can use keyboard keys or mouse clicks to move the probe. So here I'm just going to press Z, which is the depth axis. And you can see each time I press Z, the probe drives down into the cortex. And that's basically all you have to do to plan an insertion. Of course, on your actual rig, your probe might be angled in different directions. So for example, in the IBL recording, the probe is at a 15-degree angle relative to the sagittal plane, and it's on the coronal plane. So let's just recreate that. I'm going to press the keyboard key to bring the probe down to pitch it, and that key is F. So here I'm at a 75-degree pitch or 75-degree elevation, and then 1 and 3 are going to let me rotate the probe around yaw. So this is sort of the angle of the repeated site insertion. And then using W, A, S, and D, I can move the probe along the ML and the AP axis to kind of get that roughly where it was in that recording that I showed you. Let's move the probe up a little. So it's back in cortex and back into one of the visual areas. Okay, I think roughly there is the recording that we were trying to target. And again, the numbers that are coming out of here are exactly the numbers that you're going to need to recreate this recording. So on your rig, what you would actually do is grab these pitch numbers and yaw and set up your manipulator here, and then use these AP, ML, and DV coordinates to get to your entry site, and then drive down this amount of depth to reach your target area. All right. So that's it for Pinpoint demo. There's a lot of other features in here, but again, I'll point you to the tutorials to go and look at those. And I think I'll jump back to the slides and talk about some of the features that we're developing right now and the changes that are coming to Pinpoint in the future. Hopefully someone will tell me if there's any questions that are popping up.
There are questions, but do you want to take them at the end or no?
If there's one that's relevant right now, I guess I can open the Q&A. So some quick questions that I'll address now. Can Pinpoint be used to view only the mouse brain? There's also the rat brain. There are no non-human primates in Pinpoint, and I'll talk more about that at the end. Is Pinpoint only available for the 1.0 probe shape? Nope. There's a whole bunch of other stuff, and we're making it a lot easier to put other probes in. I will talk about the Atlas transforms a little later. and chronic or acute, anything that you're targeting, you'll be able to target in Pinpoint. And how do you adjust the angle of the sagittal plane? Again, I'll point you to the help to learn more about the controls. So for example, if you press escape and go to the help tab here, all the controls are listed here, and you can see that information. So I don't have to talk about it endlessly here. All right, so I'll stop there for now and answer more questions at the end, but hopefully that answers a few of the important ones. Okay, so we did this demo. Let's talk about coordinate spaces and transforms, because this is super key, and I think was missing for a lot of people when they first learned about trajectory planning. So in the mouse, so this doesn't apply to people in non-human primates, for example, we use a specific atlas to plan. The atlas is the CCF. Thank you to the folks at the Allen Institute who took a bunch of brains and created this thing. The atlas looks like this from the sagittal view and the coronal view. And anybody who's taken a brain out of a mouse would recognize that this is way too tall. The atlas is way too tall. And also the positions of bregma and lambda in this atlas are, they're actually tilted by default. So the atlas here has been untilted, basically. So because this atlas is too deep, one of the things we've done in Pinpoint is include transforms. We've taken a MRI volume from a live mouse, aligned it to the CCF, and rescaled the CCF to try to match it. And that's what's in this 2018 transform that's in Pinpoint, and is the default when Pinpoint loads. We recommend you plan in this space, but we still recommend that you use electrophysiology signatures as you're driving into the brain to try to figure out where you are, and don't just blindly use Pinpoint. If you just blindly drive down, you will hit the skull at the bottom if you're targeting deep areas, and you're going to break your probes. So it's an important note, and also just mention some quick nomenclature so you know about directions here. You can ignore this unity world space. The important one is that the coordinate space you're in, for example, the CCF, is set up so that the 000 point is in sort of the front top left corner, and the axes point posterior, right, and down. And this is how people traditionally use the CCF space and place coordinates within that space. I don't think that's useful. So we've spun the axes and put the reference coordinate, the 000 point, at bregma, which is sort of in the middle of the volume. And I showed you that in the demo, right? This is the reference coordinate at bregma. The corner of the CCF is sort of off over here. And then we change the axis directions so that they sort of match your intuition better. So just be aware of the directions of the axes and where the 000 point. The little lines here are telling you which direction the axes are pointing, the positive direction for each axis. Okay, I've got a few minutes left, so I'm going to talk about some of the things that are coming soon in Pinpoint or that are already working. So one of those is that we've been building a sort of automated robotic system for Pinpoint. So what you're seeing here is a control algorithm running that's doing the insertion process for you as part of the Pinpoint system. And the way this works is that Pinpoint, not the website version, but the desktop version that you can download on Windows or on Linux, can talk to SensApex and NuScale manipulators. This is work that was done by Kenneth Yang. And we're working to sort of close the loop on this and fully automate our rigs by using cameras to track the probes as they move over the brain surface. Pinpoint can also forward information to other programs. So there's an API that connects Pinpoint with OpenEFIS GUI and SpikeGLX, so that you can see where you are in the brain in real time as you're driving down in an insertion. Again, caution here, the electrophysiology signatures are the ground truth, not what the Pinpoint Atlas is telling you. Okay, and I think I'm gonna jump ahead a little bit very quickly. Well, we'll see where this goes. I don't think we want to do the demonstration. I did want to mention one more thing here. Okay, so the important details for all of you, if you're accessing Pinpoint from the web, which is what we recommend, you'll go to our website, data.virtualbrainlab.org and /pinpoint to load that, and I'll drop that in Slack, so you don't need to remember it right now. But feel free to screenshot it. Steam is the easiest way to access Pinpoint. It'll keep it updated over time. That's for both Windows and Linux. You can also go onto our GitHub and just download Pinpoint directly. It does run on Steam Decks too, which is something that you might want if you're in a lab and you want to be able to step away from your rig. Our website, virtualbrainlab.org, here has a whole bunch of tutorials and more information and documentation for Pinpoint. And we're adding a lot more of that very soon because version 2.0 of Pinpoint is coming out with a new user interface. So we're going to redo all the tutorials. So apologies if you find that any of them are out of date. Okay, so I'm going to switch to Q&A. I'm going to leave the demo slide up while I answer some questions, and then we'll move on from there.
Thank you
Okay,
very
so
much, Dan.
Yep.
Oh yeah, you can see the questions. One maybe that you could answer that I find particularly interesting is how does it compare Pinpoint to other planners? Because people may know about Herbs or the
Yep.
Neuropixels trajectory planner. If you could comment on that, thank you.
Yep. So if you watch any of the old videos from previous Neuropixels course, you'll see two other trajectory explorers. The sort of original one that Andy put together, and Herbs, which is another option. Both of those work great. I think we've been moving a little faster with Pinpoint and hopefully keeping it up to date, adding many more atlases into Pinpoint, adding many more probes. So at this point, I think Pinpoint is ahead of other trajectory planners and more generally useful. But if your lab is doing exactly the same thing that Andy is doing in his lab, or if you're doing exactly what the labs that built Herbs is doing, those tools will work just fine for you. And Herbs also does some other stuff. I think in the same space, you can track your electrodes, which is definitely helpful for some folks. Okay. Let's see if any of these questions. Well, I'll just go down very quickly. So I think I mentioned a little bit about atlas transforms, and I didn't mention how they relate to the Paxinos atlas. We'd like at some point to have a transform to connect you to Paxinos. For now, by the way, as part of the homework, there's a download link to the Paxinos atlas, which comes up as a big PDF like this. And the idea is that you'll also use this PDF to go find your brain region. I'm just scrolling through the PDF here until you get to the back of the brain somewhere. The idea is that you'll confirm that the position in this space is identical or more or less identical to what you got from Pinpoint. So I'll leave that exercise to you to do, and we'll talk about it tomorrow, how I would have done it. Is there a way to confirm location in vivo? Yes, you need to do that with histology. And I believe people are going to talk about that later. Nancy asked, what's the difference between DV and depth? DV is just the vertical position along the dorsal ventral axis. Depth is the distance relative to the dura surface on the brain. So when you move your probe to an entry coordinate and you touch the brain surface, depth is the distance you need to go into the brain from that point to reach your target. Does Pinpoint take into account large blood vessels, sinuses? No, we have no information about that. It changes from animal to animal. I wouldn't trust a planning software or an atlas to really know exactly where those are. You have to be paying attention during your experiments. Can we see the anatomy over the full length of the 1.0 and 2.0 probes? Yes. In Pinpoint, you can change the view of the probe so that you can see the entire probe surface all at once. If I have coordinates based on Paxinos or CCF, can I use them in Pinpoint? Yes. CCF atlas, yes. Paxinos is close enough that actually the coordinates tend to be the same. I would plan based on the anatomy in the atlas, though, and not just based on coordinates directly. I think you'll tend to do better if you try to target regions rather than just take numbers, for example, from a paper and try to reproduce them. There's a lot of questions, so some of these we're definitely just going to take on Slack rather than live, because I think probably we want to move on at some point. I'll stop the share now. Cilian and Annie, do you want me to answer more questions now or take them on Slack?
Yeah, so two things. One thing we can do is we still have like 3 minutes, so I'd suggest if you can maybe answer a few more questions if you find some that are relevant for everyone. And maybe recapitulate the homework just so that it's clear in everyone's mind what exactly they need to do. And then
Yeah,
actually you can either answer on Slack or directly on Zoom. You know, you can type an answer, I think, since you're a panelist done. And then people will get as you go if you can stay for some more time. That'd be
yep,
great.
sounds good.
All right.
Okay,
Okay. So you have 2-3 minutes. Thank you.
so I'll bring the the homework back up and mention one more time. So the homework is to first take the repeated site coordinates, which I've shown here, and plan an insertion based on those coordinates and make sure that you end up in Viz A, CA1, DG, LP, and PO, just like in the repeated site in the IBL experiment. Another way to target that exact same recording is to pull up area PO and then adjust your insertion until it goes through these target regions. And you'll need to use the angle settings to get that probe set up right. You want to be 15 degrees off the sagittal plane, so tilted sort of lateral medial, but on the coronal plane, so not tilted anterior or posterior. And I'm being deliberately a tiny bit vague about this assignment because I would like you to play around with Pinpoint and sort of discover how it works. Remember that you can always hit escape in Pinpoint, go to this help tab, and you'll have information about how to adjust the probe from there. And these examples on the right here are just showing you where your probe, the red line, should end up. Oh, and I wanted to mention in the real experiment that was done where a whole bunch of postdocs redid this over and over, they all missed by small amounts. So don't worry if you plan this trajectory and you miss by a small amount, you're in good company. And the sort of second part of the homework is that I want you to load the Paxos Atlas. You'll find a link to it on the homework GitHub. And I want you to use the PDF of the Paxos to go and find that same insertion that you did and confirm that the coordinates are roughly the same. So just a little bit of detail at the beginning here of the Paxos PDF. There are regions and sort of what page I think they end up on, which will help you figure out where you are. But basically what you do is you scroll through this PDF until you find the slice that you want to be on. And you stare at it and try to, whoops, not these slices. We want the slices that are annotated, which are earlier in this thing. Yeah, these slices. You find your slice and you figure out the angle that you want to go to and where you are relative to the Bregma coordinate. So it's a little more work, but I hope that it's kind of fun and interesting to try both of these two ways and see why we built Pinpoint in the first place.